You know, we often think of algebra as this abstract world of symbols, but have you ever stopped to imagine actually seeing the logic of a quadratic equation take shape, like right before your eyes?
Get ready for a completely new perspective then, because today we're taking a deep dive into visualizing the, well, seemingly complex process of completing the square.
And to guide us on this visual adventure, we have a YouTube video transcript and an insightful briefing document that really breaks it all down. We've done the groundwork so you can get straight to the, the aha moments.
Our mission today is to explore how this ingenious modified abacus, the Pythabacus, transforms the abstract algebra of quadratic equations into tangible geometric areas.
Think about it. Moving beads to physically create the squares and rectangles that represent X, A, B, C, X, and C. But it gets even better. This isn't just about solving equations, it's about revealing the very shape of the quadratic curve. The roots, the vertex, the y-intercept, all laid out visually. It's like unlocking a secret code to understanding these concepts. Okay, let's start by getting our heads around this Pythabacus setup.
Right. The starting point is key. Picture the Pythabacus completely reset, all the beads snug against the left post.
Yeah.
Now imagine a diagonal line slicing through the display from the top left to the bottom right corner. This diagonal is our central reference.
Exactly. Below that diagonal, our sources tell us, are 10 gold beads, and above it, brown beads arranged to form squares. Now here's where it starts to get really interesting for you. Notice how each gold bead's position along the bottom edge directly lines up with the triangle along that diagonal. It's like a one-to-one correspondence.
And as the video transcript explains, when these beads are moved, you're not just counting. The movement creates areas defined by intersecting lines orange, green, and yellow. What's fascinating here is that these areas are the direct visual representation of the different algebraic terms within our quadratic equations.
Okay, so we have the basic layout in our minds. Now let's see how this translates to a real equation. x7x plus 10x plus 4. How does the Pythabacus make this algebraic statement come to life visually?
Okay, we'll start with the Beck's term, which in this case is negative 7x. On the Pythabacus, this is visualized by taking 7 beads and sliding them from right to left. This creates a rectangular area. What's insightful for you to notice is that the dimensions of this rectangle, formed by the horizontal and vertical lines created by these displaced beads, directly correspond to the 7x term.
I can see that, a sort of stretched block representing that middle term. Now, how does the constant, the plus 10, get represented?
For the constant term, the video describes moving another 5 beads. This action creates 2 intersecting orange lines, and the area formed by their intersection visually represents 2 multiplied by 5, which gives us 10, our C1 term. So you can see, for our listener, how the physical act of moving beads directly translates into the coefficients in our equation. We've now visually constructed x to 7x plus 10.
Right. And then we have the 4 part. How does the Pythabacus show that this whole expression equals 4?
A 6th bead, counting from the right, is then pushed over. This creates intersecting green lines, and the area formed by these intersections represents the y value, which is 4 in this instance. The video uses a great visual, describing this 4 as elbowing around the orange lines that represent the 10. It gives you a sense of the equation being set to a specific value.
That's a really effective way to picture it. Now, if we want to solve our x, we need to isolate it, which means, getting rid of that 4 on the right side. How does the Pythabacus visualize subtracting 4 from both sides of the equation?
Well, the video explains that subtracting that 4, the area bounded by the intersecting yellow lines, from both sides, is done by visually removing that corresponding area on the Pythabacus. When you take away that area representing 4, the remaining area, the one still elbowing around the intersecting green lines, now visually represents the result of 10 minus 4, which is 6.
So just through manipulating beads and looking at the resulting areas, we've gone from x07, x plus 10 plus 10 plus 4, to visually representing x07, x equals 7 and 6. Now comes the part that always felt a bit abstract and pure symbol manipulation, completing the square. How does the Pythabacus make this process concrete and visual for us?
Right, this is where the real magic happens. To complete the square for x else and 7x, we need to add b2 on both sides. Here b is 7, so b2 is 3.5, and 3.5 is 12.25. Now, on the Pythabacus, we need a visual representation of this. The explanation refers to half of the blue line. Picture a conceptual blue line that represents the value of b in our equation, which is 7. Half of that blue line is 3.5 units. The area formed by a 3.5 by 3.5 square on the Pythabacus, and this is crucial for your understanding, including that small 0.25 square I mentioned, is the visual embodiment of 12.25. This is what we're effectively adding to both sides of our visual equation.
Okay, and we already visually subtracted 4 from the right side's representation, leaving us with the equivalent of -6. So when we visually add this 12.25 area, we should end up with 6.25. How does that manifest on the Pythabacus?
Exactly. After visually adding the 12.25 area, and considering the visual equivalent of negating 6 we had remaining, the Pythabacus now shows a new inner area bounded by the intersecting yellow and green lines. What's key to understand is that this newly formed area visually represents the 6.25.
Okay, I'm really starting to see how the geometry directly mirrors the algebra. So we've essentially visually transformed our equation into something that looks like by 3.5 by later of 4 6.25. Now, how do we extract the actual roots of the equation, the values of x that make it true, from this visual representation?
To find the roots, well, we take the square root of both sides of the equation. On the Pythabacus, taking the square root of the 6.25 area visually corresponds to finding the length of the side of a square with that area, which gives us 2.5. The video points out how this 2.5 visually aligns with a certain length within the Pythabacus. Remember, we also had the visual representation of 3.5, which is our B2. The roots are then found by taking 3.5 plus or minus 2.5.
Which neatly gives us the roots 1 and 6. And the video actually highlights a really neat connection here for you, the listener, right? How these roots relate back to the original configuration of gold beads and squares.
Precisely. The video emphasizes that there's a direct visual correspondence. In this example, 1 root 1 can be seen as relating to 1 gold bead in 1 square, and the other root 6 corresponds to 6 gold beads and 6 squares. It's a powerful visual demonstration of the deep connection between the physical tool, the geometric shapes it creates, and the algebraic solutions we derive.
This is truly fascinating. So we've not only solved the quadratic equation visually, but the Griefing document also mentioned that this Pythabacus can help us understand the graph of the corresponding curve. How does that work? Where do we find the vertex that you intercept all the key features of the parabola?
Okay, the vertex of the parabola, that crucial turning point, holds significant information. The x-coordinate of the vertex, as you know, is given by b2, which in our example is 3.5. On the Pythabacus, this 3.5 is directly linked to that half of b visual we discussed earlier. Now, the y-coordinate of the vertex, often denoted as k, is that inner area we visually arrived at the 6.25, bounded by the yellow and green lines. So what's insightful here for you is that the very turning point of the parabola isn't just an abstract formula, but a concrete area you can literally see on this device, giving us the vertex at 3.5, 6.25.
That's incredible. The minimum point of the parabola is right there, represented as an area. What about the y-intercept? That's where the parabola crosses the y-axis when x equals 0.
Right, the y-intercept, which is the value of c in the original equation, x must of 7x plus 10, which rearranges to xx7x plus 6 plus 6 plus 0, so c fix, is also visually apparent. The video describes it as the elbow of areas around the green lines, bounded by the yellow line. It's the area that remains after the initial bead manipulations that represent the big X and constant terms. So you can see all the essential information for sketching the graph, the roots, where it crosses the x-axis, the vertex, the turning point, and the y-intercept, where it crosses the y-axis, are all contained within this visual representation on the Pythabacus.
Okay, I'm starting to see the immense potential of this tool, but the sources also walk us through a second example. X by 7 equals 0 may. How does the visual story unfold for this equation, especially with that negative constant term?
For x on 6 by 7 equals 0, the initial setup involves moving 6 beads to represent the negative 6x term, then 4 more beads to create the initial orange lines, and finally a 7th bead for the negative 7 constant. Now, when we examine this visual configuration to find the roots, something quite interesting emerges.
What's particularly fascinating for our listener in this case?
Well, the video explains that one root can be directly observed as the total number of beads that have been moved, which is 7, and this corresponds to a positive root. The other root is found by looking at the number of beads that visually extend beyond that conceptual blue line we talked about, which represents b in magnitude. In this case, one bead goes beyond, and this visual excess corresponds to the negative root, -1. And it's a neat visual check. If you multiply these roots 7 times -1, you get -7, and if you add them, you get 6, which is the negative of our b coefficiency. A lovely visual confirmation of Vieta's formulas in action.
That's a really clever way to visualize the signs and values of the roots. What about the y-intercept for this second example? X subtotal 6 by 7 equals 0.
The y-intercept here is -7, and the video points out that this value is also directly represented within the Pythagoras configuration that visualizes this specific equation.
And the vertex for x filter 6 by 7 equals 0. Here, b is a -6, so b2 would be -3. How does that show up?
The x-coordinate of the vertex is indeed half of b, which is 3, considering the magnitude. Now for the y-coordinate, k, the video highlights that it's the area bounded by the green and yellow lines that don't overlap. In this setup, there might be multiple sets of green lines, but we focus on the ones that aren't coincident with the blue line reference. This specific area equals 16. Therefore, the vertex for this parabola is at 3, -16.
And just like with the first example, can we derive the roots of xxx 6 by 7 equals 0 from this vertex information and the value of k?
Absolutely. The roots are given by the x-coordinate of the vertex plus or minus the square root of k. So 3 to the 16 post, which is 3 to the negative 4, resulting in the root 7 and -1, exactly the same roots we found earlier through that bead counting method. It all comes together in a wonderfully consistent visual framework.
This Pythabacus truly acts as a visual bridge between abstract algebra and concrete geometry. We've seen how the simple act of moving beads creates tangible areas that directly correspond to the terms in a quadratic equation. We've witnessed the process of completing the square unfold not as a series of symbolic manipulations, but as a visual rearrangement of areas. And perhaps most powerfully, we've seen how this physical representation holds within it all the key information needed not just to solve the equation, but to understand and visualize the shape of its corresponding curve. The roots, the vertex, the intercept, all accessible through this visual language. The aha moment of seeing that direct intuitive link between the beads, the shapes, and the algebraic symbols is genuinely profound.
It really emphasizes the power of visual learning, and how even seemingly abstract mathematical concepts can have surprisingly concrete and intuitive visual interpretations. By providing a tangible way to interact with these ideas, the Pythabacus offers a much deeper and more accessible level of understanding for everyone, really.
So as you're reflecting on this deep dive, consider this. If a concept as fundamental and often taught as quadratic equations can be visualized in such a novel and insightful way, what other seemingly abstract corners of mathematics might hold equally surprising and illuminating visual representations just waiting to be discovered? And what's the potential of these kinds of visual tools to not only demystify complex ideas, but also to spark a more intuitive and lasting understanding?